So today's the day that we finally get to tie everything together. So I want to just take a look at the function of 2x. I'm going to go ahead and graph it here. So it's a linear line. So we have the function f of x equals 2x. We're going to go ahead and take a look at the area under the curve for several different portions. So we're going to take a look at what is the area bounded by this curve from 0 to 1, from 0 to 2, from 0 to 3. Then we're also going to take a look at what is the area from 1 to 3. All right, so if we think about this obviously, if we're going to find the area under the curve from 0 to 1, isn't that just a triangle? So we don't have to use our limits of Riemann sum method because it's a shape that we already know and we know how to find the area of it. So the area for this one, if you think about it, it's got a width of 1, the triangle has a base of 1, and it would have a height of f of 1. So it would have a height of 2. Now, the area formula for a triangle is base times height divided by 2. So we take 1 times 2 divided by 2, and we get 1. So the first integral has an area of 1. All right, now when we go to the second integral, we're going to go from 0 to 2. So we have this triangle. This time its base is 2, and its height is f of 2, or 4. So we're going to go ahead and we're going to take 4 times 2 divided by 2, which is 4. All right, and then for the next one, we are going to go over to 3, and again, we look at this, it has a base of 3, it has a height of 2 times 3, or 6, so it's 3 times 6 divided by 2, which is 9. Okay, I'm going to stop right there and ask if you guys see a pattern. What do you notice these numbers are? I'm hoping that you have, or that you see that those are actually the first 3 perfect squares. So let's just see if 0 to 4 would get us the next perfect square. So if we do 0 to 4 of 2x dx, so in other words, we're looking to see if this answer will be 16. Well, wouldn't the base of the triangle this time be 4? The height would be 8. And so if I take 4 times 8 divided by 2, it does indeed equal 16. So, in other words, the integral from 0 to b of 2x dx equals x squared, which is, substituting in the b, which is really just b squared. So from 0 to 10 would be 100. From 0 to 100 would be 100 squared. So that's what we're saying. And I want you to notice how these two are related. 2x is the derivative of x squared, and x squared is the antiderivative of 2x. And yes, that is significant and important, not just a coincidence. All right, so taking a look here, from 1 to 3, wouldn't that just be what we got for the first area for 3, minus the area we got from 0 to 1, because 1 to 3 means 0 to 3 minus 0 to 1. So it would be 9 minus 1, which would equal 8. And if you notice, if we use that idea with this guy, if you notice, that's just saying that we would have b squared minus a squared, which would equal 9 minus 1, or 8. Okay, so we're going to go ahead and go into some more, so hopefully we kind of follow this, but we're going to go into some more of the formality here and some of the notation. As we saw in the previous slide or in the previous example, this formula right here, we can say that f of x is a function, and to find the area under the curve, we simply find its antiderivative and subtract the value from b, or of a from b. So again, we find the antiderivative, and then we just plug in b and a, and that gets us the exact answer. So guess what, you guys? No more limits of Riemann sums. It's just this simple. Now, if we say indefinite integral, remember when we find an antiderivative, we have to have the plus c on it. So when it's an indefinite integral, it means that we don't have the a and the b, and we have to have our plus c. But when we have the a and the b, and I'll show you in the next section why that works, but when we have the a and the b, the constant won't matter at the end. So it's all good. But for this, we have to put our plus c. All right, so we're going to go ahead and use that idea to find this next example. Now before, when we translated this into a limit of Riemann sums, we found our change in x, which was 4 minus 1 over n, or 3 over n. We found our x sub I, which was 3i over n. In this case, we'd have a plus 1. And then we found our function of xi, which again in this case is going to be e to the 3i over n plus 1. So kind of a mess. And it's not going to be super easy to get that I on its own inside the summation. So instead, we're going to use this new idea that we just discovered, and that is that we can simply just take the antiderivative of e to the x and plug in the 4 and the 1 and subtract their values. So bringing this guy down here, the antiderivative of e to the x is convenient because it's e to the x. A notation that we use is we use the little bracket there, and we say from 1 to 4. So we're indicating this right here means we found the antiderivative, but we have not substituted in the a and the b yet. And then we say that that equals, substitute in your b, and then substitute in your a, which would be e to the 4th minus e. And it's that simple. All right, we are going to do the next example here. Again, this just says find the general indefinite integral, or general form, so there's no a and b. That's what's missing here, and whenever you're missing the a and b, we need to remember to put the plus c. So on this guy, we have, if we do the antiderivative of this, we would have 10x to the 5th over 5 minus, and remember that secant squared is the derivative of tangent. So I know its antiderivative is tangent, and because this is an indefinite integral and there's no a or b, we're going to put a plus c. So really, it's 2x to the 5th minus 2 tangent x plus c. And it's done. That's it. That is our formula for the area bounded by that curve in the x-axis. All right, you're going to remember this little guy. We did this guy in each way. We used this guy to do left and right endpoints. We did not do midpoints with it, but we did also do our first limits of Riemann sum and taking the limits and everything of this one. So we're going to go ahead and see how this works using our new method. So again, we are going to take the antiderivative of this. The antiderivative would be x to the 4th over 4 minus 6x squared over 2. And that is going to be evaluated from 0 to 3. So I'm going to go ahead and simplify it before I do the evaluation. 3x squared here from 0 to 3. All right, and remember we did this the first time with 6 rectangles, and then like I said, we did it with infinite. So we're going to go ahead and take a look at what happens here if we plug in the 3. So to go ahead and evaluate this whole thing, we first plug in the 3. So it'd be 3 to the 4th over 4 minus 3 times 3 squared. So I just plugged in the 3. Then I subtract from that, plugging in the 0. So 0 to the 4th over 4 minus 3, 0 squared. Obviously, this will all go to 0, but I just wanted to show you what it kind of looked like. Sorry, it's supposed to be parentheses. Okay, so we really just have 3 to the 4th, which would be 81 over 4 minus 27. And I would encourage you to go back to your notes on that one that I told you that you're going to need a separate sheet of paper for. And I bet you're going to see that these were the two coefficients inside the Riemann sum that we were able to pull out once we did the limit and got everything to go to 1, everything else to go to 1. We had 81 over 4 minus 54 over 2, which we reduced to 27. And then we can go ahead and evaluate that and get an actual answer. And we found earlier, which we'll show right now, that this equals negative 6.75. So again, look at how short this process is, and now I know you're all going to hate me because I didn't just show you this first. But hopefully you can understand how we evolved from the limit of Riemann sums into being able to take the antiderivative to find the areas bounded by the curve. All right, I'm going to go ahead and move this guy up. And we're going to do this next one. All right, so we're going to do the antiderivative, and we would have 2x to the 4th over 4 minus 6x squared over 2 plus, and I notice that this is just 3 times the derivative of arc tangent. So I know that this is going to be 3 arc tangent x. And I'm going to evaluate that from 0 to 2. All right, so I'll reduce first. So I get x to the 4th over 2 minus 3x squared plus 3 arc tangent x from 0 to 2. Now if I go ahead and plug 2 into this, because that's what I do first, I first plug the 2 in, then I will minus plugging in the 0. So plug in 2, I get 2 to the 4th over 2 minus 3 times 2 squared plus 3 arc tangent of 2. And then minus, and again, parentheses are important here because you're minusing the whole thing. We would have 0 to the 4th over 2 minus 3 times 0 squared plus 3 arc tan 0, which this will all go to 0, obviously. So really, for our final answer on this, we just need to evaluate this part here, which when I do that, I get, see, it looks like negative 4 plus 3 arc tangent 2. All right, and that would be the antiderivative. That would be the area under the curve, the exact area under the curve from 0 to 2 of that graph. All right, this will be our last example. This one is a little more complex. So now that we've kind of got the idea down, hopefully, in the process of the way we do things, this one, remember we talked about you can't take an antiderivative at this point anyway. I'm going to show you in a couple sections how to do it, but at this point we can't take an antiderivative if we don't have a bunch of terms being added and subtracted together. So in other words, if we have a product of two terms or a quotient, it's a rational function. It's not going to work. So we have to look for another way. On this one, I noticed that everything in the numerator is divisible by t squared, or by the t. So I'm going to go ahead and separate everything. So I have 2t squared over t squared plus t squared square roots of t over t squared minus 1 over t squared. All right, so the first one will just become 2. The next one will just become t to the 1/2. And the last one will become t to the negative 2. All right, so I've rewritten my integral as this. And now it's something that I can actually take the antiderivative of. The antiderivative of 2 is 2x. Of t to the 1/2 is t to the 3/2 over 3/2 minus t to the negative 1 over negative 1. And that's going to be evaluated from 1 to 9. And again, we can do some simplification here. So we have 2x plus 2/3, because when we divide by a fraction, we really multiply by its reciprocal, t to the 3/2 minus, or I'm going to make that plus, t to the negative 1. And that is from 1 to 9. All right. Our last and final step is plug in 9, then plug in 1. So I'll get 2 times 9 plus 2/3, 9 to the 3/2 plus 1 over 9 minus, and remember put your parentheses, 2 times, now we're plugging in 1, plus 1 to the 3/2 times 2/3 plus 1 over 1. All right, so it looks like we end up with, if I go ahead and do this, I get 18 plus 18, because 3/2 of 9 is going to be, square root is 3, take that to the 3rd power, you get 27, and then that's reduced with the other 3 on the outside, so we end up with 18, and then plus 1 over 9, minus, let's see, this in here goes to 3 2/3. All right, and so it looks like when I'm done, I get 32 4/9. So that would be the exact area under the curve. Again, the biggest problem with this one is you have to separate all those terms. You can't have the rational function to do this. All right, hopefully you guys will enjoy this homework. I think after all the tediousness of the last two sections, this one is going to make your lives a lot easier. All right, we'll see you later.